guys, a very happy morning to one of you. And guys, now we are just going to see the production engineering, the next classes. Okay, so before going to the classes, let us have just a 5 minutes of revision. So after 5 minutes of revision, we can just go into our part. Okay, so metal cutting. So in this thing, I just explained to you before. Okay, so you can see deformation plastic only, and cutting tool accesses, machine tool lathe, manufacturing process converts raw material to finish. Okay, production process converting input to output, and machine tool non-portable. So these are the things I just told. This power up reasonably valuable device, and it is also cutting tool must be there. Okay, and 3 phases. Since it has 3 phases, it has 6 angles. Okay, so first one is back rake angle. Back rake angle 2 times B, it means BS 2 times of ES. Okay, next one is end relief angle, side relief angle. Okay, next one is end cutting edge, side cutting edge. Next one is nose radius. Okay, these are the things that are so much important to me. Okay, so next one you can see we measure based on machine reference system. Entire thing, this entire whole thing is measured based on machine reference system. Okay, it is ASA, American Standard Associated Tool Signature. Okay, it's not tool based. Okay, it's telling machine based. Okay, I think you have got the point. So you can see at it means top, it means from the top you see image, you can see this is end cutting edge, it's a small one. This is a principal angle. So this one is a side cutting edge. Okay, this smaller thing I think so you can see this is nose radius. And whenever you just see from the front, it means from this side, you can see this is side rake angle, this is end side relief angle. Okay, entire thing is side. Okay, when you just see from this point of view, side point of view, you can see this is back rake angle, this is end relief angle. Okay, back rake and end relief. Okay, you can see relief both exist in this phase, and rake exists in the top phase. Okay, I think so you're getting the point. So next you can see ASA is a tool signature, shows only the angles. So orthogonal rake system for force and is a tool reference system. Okay, so I think so you can understand. So side cutting is prevents interference to the workpiece. When side cutting edge angle, it means this side cutting edge angle increases. You can see separation from the workpiece definitely will be there. Okay, I think so about the point. So and it also induced chattering sound, and as a value to the length of chip increases, and with the tip and heat dissipation flow increases, but and also tool life also increases. But the main thing is, since the tool life is also increased, so separation from the workpiece will be so much higher, and the vibration will be so much higher. Okay, I think you can understand. So since suppose you can see, since the CS will like this will go. Okay, since it has been like this, force also we need to just give a lot. Okay, I think you can understand. Okay, so next one you can see this one is cutting force, this one is thrust force. So it means, and it means thrust force 0 means no contact with the tool workpiece, and FC the removal of tool workpiece material. Okay, next one force analysis, ORS, orthogonal rake system. So tool signature. Okay, you can see entire thing force analysis we just go with respect to tool signature. It means first one will be the inclination angle, next one will be the orthogonal rake angle, next one will be the side relief angle, end relief angle. It means S I alpha C lambda of n. Okay, no cities. Okay, so relief only will come. Okay, here no rake will come. Okay, only orthogonal rake will become. Okay, so when inclination angle is completely entirely equal to 0, it is called orthogonal cutting. Okay, I think so got the point. So if this inclination angle equal to 0, it is orthogonal, it means cutting. Okay, if it's not equal to 0, it is oblique cutting. Okay, just a simple basic principle. So back rake angle, side rake angle, tool angle only say ASC, but force analysis I and alpha, this comes and we get the force analysis. Okay, so I think so got the point. So this thing, it means theta directly proportional to strength and inversely proportional to sharpness of cutting edge. Okay, so I just explained about positive rake angle, negative rake angle, and zero rake angle. Okay, each and everything I just explained. So positive rake angle, negative rake angle, and minus each and everything I just explained to you. Okay, I think so you're getting the point. Just one second. So you can see positive rake angle, negative rake angle, cutting force, each and everything I just told to you, and positive rake angle, machine strength low and low power cutting tool accesses. So, okay, so negative rake angle, cutting force is so much, and we use cutting tools ceramics and carbides. So negative rake angle means negative rake angle, you can see no cutting, it means everything will be discontinuous chips. Okay, if used, you can see it means yes, no cutting of the low strength. It means no cutting of the low strength means if you just cut low strength only, so long continuous ribbon chips will form. So Positive is, you can see, soft and ductile. So positive, soft and ductile. So negative, it is hard and brittle. Okay, I think so you can understand. So it's some toughness good. Okay, and then tool bits is being used. Okay. Okay. So these are extra things. So before telling you can see this one is depth and this one is width. Okay, this one is cutting edge and this one is lambda. Okay, based on this you can just calculate this one. Okay, so you can see important formula T equal to D. It means thickness equal to depth of cut equal to orthogonal metal cutting. Okay, 2 dimension. So just turning. Okay, just turning means equal to T equal to f of sine of lambda. Okay, T equal to f of sine of principal angle. This is turning. Okay, 3D and orthogonal turning. Okay, orthogonal only 2D. So you can see T equal to f of sine 90 degree. Okay, so stress equal to force by area. Okay, so generally you can see chip thickness is greater than uncut chip thickness. Okay, due to shear failure that chip thickness will be so much high due to shear failure. Okay, and also due to the thermal expansion. Okay, so speed equal to pi dn divided by 60 meter per second. So if meter per minute means pi dn. Okay, that's it. Okay, I think you got the point. Next one, feed velocity. Feed velocity equal to feed into rpm. Okay, feed velocity is feed into rpm. Okay, you can see feed, this one is velocity, just multiply and get the answer. Okay, that's it. So feed due to cutting tool. Okay, so next rpm due to workpiece. Okay, so feed velocity is this one. Okay, feed equal to due to the cutting tool. Okay, rpm is due to the workpiece. So next one, depth of cut d equal to d1 minus d2 divided by 2. Okay, so next you can see r. So cut, it means cutting area is equal to t divided by tc, lc by l and vc by v, and next one is equal to sine shear angle divided by cos of shear angle minus of alpha. Okay, normal thing. So this is mainly what tan pi equal to r of cos alpha divided by 1 minus of r of sine alpha. So this one is the shear angle. Okay, r is the chip thickness ratio, cutting ratio, that's it. Okay, so r less than 1. Okay, I think so you can understand. So tungsten to chromium and vanadium, you can see 18:4:1. This is the most important ratio, tungsten, chromium, vanadium. Okay, I think so you can understand. So you can see next one, shear strain. Okay, I think so you are able to see this one. Okay, shear strain equal to gamma equal to cot shear angle plus of tan of shear angle minus of alpha. Cutting velocity is cutting tool with respect to workpiece. Okay, chip velocity chip tool, chip with respect to tool. Shear velocity chip with respect to the workpiece. Okay, so velocity angle is also important one. Okay, v it means cutting velocity by cos of shear angle minus of alpha equal to shear velocity, it means shear velocity of cos of alpha, it means orthogonal angle equal to, it means chip velocity to be sine of shear angle. Okay, that's it. So you can see for minimum shear strain, it means for minimum shear strain to occur, you can see 2 pi minus of alpha equal to 90 degree. Okay, suppose if a material has larger shear strain means the force conception will be so much higher. Okay, that also so much important thing. Okay, so minimum shear strain is this one. Okay, it means shear angle equal to 45 plus of alpha by 2. Okay, so next one is shear strain rate. Okay, shear strain rate equal to shear velocity divided by thickness of primary shear zone. Okay, okay, I think so we understand. So in the primary shear zone, the fluid, it means it generally acts as a fluid. Okay, so primary zone, secondary zone, I just told. So this one I just effectively told you. Okay, this one is by alpha, this is 90 minus of beta, this one is beta. Okay, next one is tan beta equal to nu. Okay, I think you got the point. So this one tan beta, equal to tan beta equal to nu. This is the most important thing. Sometimes people get confused in this. Okay, so next one you can see, whenever the force is given like this, what is this, force equal to v. Okay, alpha equal to 0 means f equal to n and f equal to nu. So f equal to nu of n. Okay, so nu equal to 1. Okay, I think you got the point. So these are the extra thing. It means guys, until now for Merchant cycle, if they ask one force, we can calculate the one force based upon this one. Suppose if they ask two force, they need to calculate two force, means based upon this relation we are just going to calculate two force. Okay, so different thing. Okay, do not get confused. Okay, so you can see Merchant first solution. Merchant first solution means this is the thing. It means shear angle of 45 plus of alpha by 2 minus of beta by 2. Okay, okay, so so geometrics, I think so I can it means geometric is just cross section area, diagram means directly cutting that. Okay, so geometrics means you can see it is circular and diagram means it is linear. Okay, so this one is normal thing. Okay, just go and start our classes. Okay. I think so. We just left the thing from here. I think so. So let us read the question and we can just continue. Okay. So you can see in orthogonal cutting is given HSS tool having tool signature. Okay, tool signature orthogonal reference system. Okay, each and you can see inclination angle, orthogonal angle, everything is given. So shear angle for PD above cutting force. Okay. So what will be the answer? So this one how we can just calculate? So tan pi equal to r of cos alpha minus r of sin alpha. Okay, so you can see what is r equal to t divided by tc, lc by l, vc by v. Okay, so how we can just calculate that? You can see width of cut, no. Shear, okay, no. Depth of cut is 0, depth of cut thickness equal to 0.25, nu equal to 0.7. Okay, so alpha is 10 degree, inclination angle equal to 0 degree. Okay, how we can calculate the r? Okay, so this one you can see tan beta equal to nu. Okay, beta equal to tan inverse of 0.7. we can just calculate the beta, and alpha equal to 10 degree. We just both of the two things we know. So how we can calculate the other thing? Shear force equal to shear stress into BT1 divided by sin of pi. Okay, side equal Laplace gravity by. Guys, somewhere we are missing just a simple thing only. So you can see how we can calculate width of cut. Okay, it is orthogonal cutting. So alpha, so suppose if we just calculate with this one, it means 45 degree plus of alpha divided by 2 minus of beta divided by 2. 45 plus 5 minus of tan of 0.5. Tan inverse 0.734. Okay, minus, so 50 minus of 50 equal to 15 degree. So you can see, so definitely this can't be valid. Okay, so what could be the other possibilities? So divided by 2, put here and calculate the answer. That's it. Simple mistake. So next question is this one. In orthogonal cutting, so the minimum power required. Okay, so power equal to what? Cutting force into cutting velocity. Okay, so okay, since they have just given this one, we need to calculate the cutting force. Okay, and cutting speed, you can see cutting speed is 150 equal to 150 meter per 60 seconds into cutting velocity fc. So generally this one, so since you can see we can calculate this one, so fs we can just calculate easily. Okay, so this one is fs C, this one is ft, this one is f, this one is n. Okay, this one is beta. So first, after calculating fs, calculate the radius. Okay, this one radius length. Okay, this radius will be like this. Fs, this one will be pi plus beta minus of alpha. So based upon this, calculate the radius. After calculating the radius, we need to just input this. Okay, fc, ft, this one is radius. So this one is beta minus of alpha. As radius we just we can calculate the fc. Okay, that's it. Okay, after calculating it will become so much easy to calculate each and everything. Okay. Page number 22. So I think you can see this one. So for the first you need to calculate fs, this one. Okay, after that fs we just put in the radius and we calculate the radius. Okay, radial force. After calculating we put here and cutting force. So later on multiply with this one and we will get the required answer. Okay, that's it. Simple question. Okay, you can just go for this one. It has been asked in 2004. Okay, 2014. A pair of following is cut for orthogonal cutting using single point tool. Okay, reduction angle, friction angle. So you can see frictional angle is beta. Okay, so frictional angle, they just interrelated this frictional angle with respect to fc. Okay, so let us, what is the formula of fc? Fc is compared with the radius. Okay, opposite adjacent hypotenuse. So sin cos theta equal to fc divided by of radius. Okay, cos fc equal to radius into cos of beta minus of alpha. Okay, let us suppose r is 1000. So cos friction angle is being increased, cos is 50 minus of 10 degree. So second 1000 cos 40 minus of 10 degree. So I can say this one is 40 degree, this one is 30 degree. So wait, cos 40, this one is 0.7660. okay, cos 30, you can see this one is 0.866. so while we are, you can see, while we are decreasing the friction angle, the cutting force increases. Okay, so reduction in the cutting friction angle leads to increase in the cutting force. Okay, okay, so next one you can just see, so reduction in the friction angle increases chip thickness. So how we can interrelate this chip thickness with this one? Okay, so this one, guys, I'm 100% sure, but I don't know why I'm getting a negative point of view against this one. Okay, answer is D. Maybe we have did enough mistakes in my part of everything. So what they have just given, you can see. I think so you can able to see this one. So it means since the friction angle has been reduced, so this entire value will be keeps on increasing. Okay, as shear angle increases, the cutting force will decrease, and length of the shear plane decrease results chip thickness reduction. Okay, I think so got the point. So answer is D. Okay, next one you can see better surface finish obtained when the large rake angle, because area of shear plane decreases and leads to, so the area of shear plane decreases, resulting in the decrease in the shear force and cutting force. Maybe this one. Yeah, is one. Okay, so the tool becomes thinner and the cutting force also reduced. Okay, so I'll just explain this question once again in later point of time. So next one you can see modified merchant theory. Okay, this one is other modified merchant theory. This one is not that much as, but you just keep in your mind 2 shear angle plus of beta minus of alpha equal to cot inverse of k. Okay, that's it. So you can see answer is B. Okay, so 2 times of shear angle plus of beta. Okay, 2 times of shear angle plus A, this one. So gamma is friction angle and alpha is rake angle. Okay, so next one you can see theory of Lee and Schaffer. Okay, so based on slip plane field theory, so some people might have what is slip plane field theory. So you can see they applied the theory of plasticity. Okay, for ideal rigid plastic body. Okay, they also assumed the deformation and thin shear zone. Okay, you can see slip plane field theory is to analyze plastic deformation ductile material like under plain shear condition. Okay, assuming the body obeys ideal plastic, no elasticity and no strain running is occurring. Okay, in simple words, it is used to determine stress, velocities and flow pattern in metal when they are deformed plastic. That's it. Okay, I also can understand. Okay, so yield condition is stress condition and the maximum shear stress is direction of slip plane. Okay, that's it. So you can see application based upon slip plane only, the extrusion, forging, drawing and indentation problems have been carried. Okay, okay. So it means the theory of Lee Shafter means, suppose if they asked in the question Lee Shafter principle, tell me the formula, means this is the entire formula. Okay, so shear angle equal to pi by 4 plus of alpha by beta. Okay, this is the angle, this is the formula, pi by 4 plus alpha divided minus of b. Okay, so this is a Stabler equation. So if they asked about Stabler means pi by 4 plus alpha divided by 2 minus of beta, that's it. Okay, so next you can see this is force relationship. Okay, in the question they will ask two force and they will just ask us to calculate the each and everything. Okay, I think so you can understand. So this one is such a simple thing, guys. So it means put F N, it means normal force and shear force. Okay, equal to same thing. Okay, see entire thing FC FT and FT sin. Okay, entire thing is sin alpha, it means sin cos sin cos sin, it means cos sin. Okay, this one is sin alpha, this one is cos alpha, next one cos alpha, this one is sin alpha. So here shear angle, here shear angle and here shear angle. Okay, sin of shear angle, so plus minus. Okay, that's it. I think so you can understand. So you can see here two forces they have just given here. Okay, so two forces mean what I just told. So whenever the two forces is given, we need to just calculate the force relations. Okay, this kind of thing. Okay, so you can see what is the cutting force given, thrust force is given. So shear angle given 30 degree, they are asking in the shear force. Okay, so Fs is this one, Fc cos shear angle minus of Ft sine of shear angle. So FC is 900 Newton cos of 30 minus of FT is 600 Newton of sine of 30 degree. Okay, just put here and calculate the answer. Okay, that's it. So next one, this one you can see. So in orthogonal cutting operation, shear angle is this one. Okay, so cutting force and thrust force given, the shear force will be predominantly Fs they are asking. So Fs I think so you can know, it means the same thing as we did it before. And in orthogonal cutting, the cutting force and thrust force are given 1500 Newton. Oh, the alpha is 0, they are asking the coefficient of friction. So coefficient of friction is nu equal to F divided by N. Okay, so you can see F and N. So just Fc sine of alpha minus plus Ft cos of alpha by Fc cos of alpha minus Ft sine of alpha. So but alpha equal to 0 degree. Okay, so actually you can see orthogonal cutting process 0 degree, it is a regular. So each and everything is good. Okay, that's simple thing you can easily calculate. Okay, so next one is this one. You can see in orthogonal turning 60 mm diameter bar is observed that a tangential force. Okay, feed force also given. Oh, tangent cutting force given, so feed force is given. So is the tool like in the question of, so they are asking the new. Okay, so cutting force is what, 3000. So feed force is Ft. Okay, that's it. So you can see it, I just showed it to you. So you can see this one, cutting force, feed force is thrust force, that's it. Okay, so next one you can see in orthogonal, so cutting force, feed force given, tool direction, cutting speed, depth of cut, chip thickness, friction angle between the machines. So they are asking the friction angle nu. So nu is how much? So what I just will beta. So tan beta equal to nu. Okay, so B equal to tan inverse of nu. So nu is F divided by N. Okay, calculate F divided by N and put here and take the tan inverse, you will get the answer. Okay, that's it. Okay, so now we can just start the next thing. Okay, so you can see in this one, they are cutting force, each and everything they are asking the cutting speed. Okay, just chip speed. So VC they are asking. So how we can just find the VC? It means V divided by cos of shear angle minus of alpha equal to VC divided by sine of alpha equal to VS divided by cos of shear angle. So chip speed. Chip speed, just think guys how we can just calculate. Cutting force given rectangles, so cutting velocity is okay. So first we need to calculate the shear angle. Okay, cutting is force. Okay, whether, so I can see orthogonal rectangle is centrally 0. So since if it is 0 means what will be there? So cutting force will be equal to normal and thrust force will be equal to frictional force. Okay, so frictional force equal to, so thrust force equal to F. It means so I think so you can understand simple thing only. So it means 500 Newton equal to, it means wait. So you can see this is the friction force. Okay, so this is a normal force and the respective means shear angle. Okay, this one is a normal. Okay, okay, so guys, what could be the answer? So thrust force. Okay, here, so let us suppose tan of alpha equal to R of cos alpha divided by 1 minus of R of sine this one. So it means R is what? Depth of cut and chip thickness. Okay, so R equal to 0.8 divided by which one? 1.5. Okay, TWDC, calculate the shear angle. So after take these two things and calculate the remaining. Okay, I think so. Can answer. Next one you can just they are asking the shear angle and shear force. Okay, shear force is such a simple thing. It means since they have just given normal force, it means normal force is cutting force. Thrust force is this. Okay, so FC equal to, it means F is equal to which one? FC and FT. So this one will be cos, this one minus cos sine. So shear angle. Okay, so FC shear angle we just now put here and calculate the shear force. That's it. Okay, so I think so you are able to understand. So this one you can see, or we just calculate and calculate this one. Okay, just 1 second. So 37, slide number 37. Okay, you can see this one. Oh, they just calculate basically upon this small thing, article TWDC is this thing. Okay, so these are got the point. So next question you can see this one, ultimate shear stress. So F is equal to tau s into B into T1 divided by sine of this one. Okay, with the given. Okay, calculate this one. That's it, finished. So about next one you can see, during orthogonal measuring, T1 chip thickness. Okay, with the cutting force, determine the coefficient. Okay, so okay, this one I think so I can easily do it. Okay, so IFS. Okay, depth of cut chip thickness with and okay, this also you can do. So you can see merchant first solution. Okay, merchant first solution means what will be there, 45 plus alpha divided by 2 minus beta divided by 2. Put here and calculate 10 degree and so the coefficient of friction at the chip. So they are asking the coefficient of friction. So they are asking the nu. So nu equal to how much? So tan beta equal to nu. So since they are asking the nu, how we can just find the nu? Uncut chipness. So R we can just calculate and you can see this one. So alpha. Okay, using merchant for the minimum cutting force. Alpha divided by 2 beta. Okay, no extra thing is given. So I think so we need to just interlate these two formulas and calculate. Okay, so 2019. Okay, or calculate, yes, as I just told before. So you can see tan theta equal to r of cos alpha divided by r of sine. So calculate theta, it means shear angle, put the shear angle here and calculate the beta. That's it. Okay, so just a simple question, you can just do it. Okay, so next we can see assuming merchant theory. Merchant theory, you can see the energy of total energy dissipated due to friction. It means total energy is how much? So suppose you can see it means friction. So definitely friction force with respect to chip velocity. Okay, so friction force into chip velocity divided by, it means cutting force into cutting speed. Okay, calculate this one and we will get the answer. Okay, that's it. So you can see this one. So total power equal to this one, FC into V, this one 400 watts, and frictional power equal to friction force into VC. Okay, cut chip velocity. Put here and calculate and just divide it and we will get the answer. Okay, that's it. Okay, so next thing you can see shear angle. Okay, shear angle and shear strain. So what is the shear strain rate? Shear strain equal to cot of gamma, cot of pi plus of tan of pi minus of alpha. Okay, I think so we're getting it. So put here and calculate. Oh, okay, that's it. see guys, what's the main thing here is since the question is literally so much higher here, so that's why it means going so much longer. Okay, so we'll be going to see about the tool life. Okay, so tool life I just explained to you and each and everything, tertiary wear at the end will occur and each and everything. Okay, flank wear and critical VLN. Okay, so cutting tool. So before that, just wait for 1 second. Just I think so you are able to see this one. So generally, mostly failure will occur with the flank wear only. This the thing will be respect to the flank wear will occur. So the rake surface definitely the wear will be okay, but the flank is so much important. So I think so you can easily measure this one, x2 minus of x1 and y2 minus of x1. Where you can see it means to find this one y minus of y1 divided by y2 minus of y1, or x minus of x1 divided by x2 minus of x. So based upon this you can calculate the each and every thing. Okay, so next you can see tool life area ISO. You can see uniform here 0.3 mm average all over and localized peak is 0.3 and individual per. Okay, so you can see generalized, it means whenever we have little bit of problem, no problem. So you can see guys, whenever asked in between means it is interpolation. Okay, whenever it's asked above means it is extrapolation. Okay, based on that we need to just calculate everything. So crater we can see more common in decline material which produces continuous chips. Okay, crater wear also occurs on the rake face at a very high speed. Crater wear problem knowledge. For crater wear temperature is the main culprit. Yes, definitely for crater wear temperature is the main culprit, and tool diffuses into chip material and tool temperature is maximum at some distance from the tool tip. Okay, for crater wear temperature is main culprit. Okay, for crater wear temperature is main culprit. Okay, so you can see crater wear distributes a linear increase with the time. Okay, so it increases material removal. Crater wear increases with material removal. So crater wear has little or no influence on cutting force, workpiece, total the surface finish. Crater wear the tool always starts at some distance from the tool because temperature is maximum. Okay, I think so you can understand. Okay, so why does crater wear start at some distance? Because the tool temperature is maximum in that distance. Okay, in that region. So crater wear starts at some distance because the tool temperature is maximum at that region. Okay, crater wear is predominant in. So generally you can see crater wear is predominant lesser temperature. You can see tungsten carbide materials. Okay, so I think so you understand. So ceramic tool is not a metal. Okay, but high speed steel. Okay, is a carbon steel. So metal and metal diffusion will occur in the ceramic. Okay, so ceramic no diffusion occur. Okay, so generally B is the best thing to be just auditor. Okay, so next one you can see wear mechanism. So abrasion wear, and you can see in this. So it means to explain clearly, I'll just explain to you. Just 1 second. ABRES. So you can see abrasion wear, the loss of material caused by hard and rough surface sliding and rolling against a softer surface. Okay, so you can see, so two types. You can see this is a hard material, this is soft material. While just moving this kind of thing, the abrasion wear definitely occurs. Okay, so I think so you're getting the point. So this is abrasion wear. So next one is adhesive wear. Okay, so it is a type of wear that occurs to sliding atomic bonds. Okay, it means adhesive wear is here while we are just rubbing two materials, micro welds is occurring. Okay, micro weld is occurring. So diffusion wear means, so generally two materials started to diffuse. Okay, D I F F U S I diffusion again. So you can see the wear mechanism of the cutting tool, where the atom from the tool and workpiece exchanges at item. Okay, next one is chemical oxidation. Means very oxidation means what will happen. So generally if aluminum is kept in pure metal means it will get oxidized so much easily. Okay, that is oxidation here. Okay, so plastic deformation as occurs. So 1 2 3 this one. Okay, this one I think so you can do, and you can see that type of with the cutting action. So the type of way that occurs in cutting action of particles in this one is erosion wear. Okay, next is absorption and so before going to this thing, I just wanted to tell you this one. Okay, you can see Taylor's two-life equation. This is the most important. Okay, so here time is, so it means velocity t power n equal to constant. Okay, velocity t power n equal to constant. Okay, so t is time is in minute. Okay, n is exponent, depends on tool material. Okay, they will just give in the question, and c is constant based on tool and work material and cutting condition. Okay, so C depends on each and everything. So it is just Taylor's two-life equation is entirely based on flank wear. Okay, I think so I can answer entirely based on flank wear. So n equal to, it means for HS equal to this one, for carbide equal to this one. It means see, this usually they have been asking this one. For ceramic only it will be so much higher. Okay, so you can see for Taylor's we have the C depends on which one. So n is depends on tool material. Okay, n is depend on tool material. Okay, so 2 and the tool material will be next one. You can see tool or work material cutting condition. So each and everything. So what will be the answer? 1 2 3. Okay, so for ceramic you can see it is C. Okay, so these are the extra things I just wanted to tell to you. Okay, maybe still 2 classes I think so we'll just cover this extra thing. So you can see why chipping off or fine characters developed at cutting edge. Tool material is too brittle. Okay, work design of the tool such as high positive rake angle, as a result crack that is already in the tool. Okay, excessive stress, static and strong loading of the tool. Okay, so next thing you can see notch wear on the trailing edge is to a great extent on oxidation wear mechanism occurring by the cutting leaves tools being the. So this one is just happening afterwards. So notch wear means it is smaller wedge, it means smaller tip that makes cut off. Okay, oxidation occurs due to oxidation. Okay, so okay guys, then I'll just explain you in the next video. Till then, take care, bye bye, have a good day.